The aim of this video is to understand a new method for solving quadratic equations, and that's called completing the square. We will also practice applying it. But first of all, let's build the idea towards the full completing of the square. If, for example, you want to solve x squared equals 4, you can take the 4 to the left hand side and make it a difference of 2 squares, but there's an easier way. You can take the square root of both sides, and that would give you x, which is equal to plus or minus the square root of 4. Don't forget the plus or minus, and that equals plus or minus 2. This is simple enough. If, on the other hand, you have something like x plus 3 all squared equals 16. We take the square root of both sides, same way, and we are lucky because the left hand side is a perfect square, just like the x squared was in the previous example. It's something raised to the power 2, so obviously you can take the square root of both sides. This gives us x plus 3, and the square root of 16 is plus or minus 4, so obviously x is equal to, by subtracting 3 from both sides, and that equals negative 3 minus 4 is negative 7, or negative 3 plus 4 is 1. So those are the two solutions of this equation. If, on the other hand, we have this equation to solve, again we take the square root of both sides, and that gives us x minus 4 is equal to plus or minus the square root of 20. Now it's true that 20 is not a perfect square, but it doesn't really matter. Then by adding 4 to both sides, x is equal to 4 plus or minus the square root of 20, and if you want to put it in the simplest radical form, it equals 4 plus or minus, this is 4 times 5, 4 goes out of the root as 2, so 2 root 5. And if you want to evaluate it to a certain number of decimal places, you just simply punch it on the calculator. So, these problems are easy because the left hand side is a perfect square. They were presented in a form that allowed us immediately to take the square root of both sides. So let's look at perfect squares. You know from expansion that x plus a all squared, which is a perfect square, when expanded takes the form x squared plus 2ax plus a squared, and that x minus a all squared, when expanded, takes the form x squared minus 2ax plus a squared. So we have 3 remarks. The first is that the constant term in the expansion is always positive. This is positive and this is positive, even though the sign inside the bracket here was positive and here it was a negative. The other very important remark is that if you take half of the coefficient of x, in this case the coefficient of x is 2a, and you halve it, you get a, and you square it, this is what you get, the a squared, the constant term. And if you take the coefficient of the x term, which is negative 2a, you halve it, you get negative a, and you square it, negative a all squared is a squared. And this is the key point behind this method. The coefficient of x halved and then squared will give you the a squared, and this is a sign that this expression is a perfect square. And finally, keep in mind that in this example and in this context, the coefficient of x squared is 1. So any conclusion that we make will be related to the case where the coefficient of x squared is 1. So let's ask ourselves, What would make the following expressions perfect squares? Obviously, x squared plus 6x is not a perfect square. It needs a constant to make it so. What do we do? What's the coefficient of x? It's 6. Half of it is 3. Square the 3, you get a 9. And immediately you will know that this is a perfect square, and you can factorize it as x, root of the first, sine of the second, root of the third, and that's it. What would make this a perfect square? Half the coefficient of x is negative 6. Square it, you get 36. And it's a plus. And then when you factorize it, it's x minus 6 all squared. In this case, half of the 8 is 4. Square it is 16. And obviously, this is x plus 4 all squared. Here, obviously 25, giving you the two factors, a repeated factor of x minus 5 all squared. And then we have to add half of the 3, which is 1.5, and we square it. We don't even need to calculate it. Just write it as 1.5 squared. And when you factorize, this is x plus 1.5 all squared. Same idea here. You add half of the 5 squared, 2.5 squared. You don't even need to calculate this. And this would be x minus 2.5 all squared. So now we know that if we have an x squared term and the next term, we know what the constant that needs to be added in order to make this expression a perfect square that can be written in this form. So, the steps for solving by completing the square. For example, if we have x squared plus 6x equals 7. The left-hand side is not a perfect square, but we can make it so by adding a constant. And we have just seen how to add this constant. Let's add a 9. But this is an equation. And in order to maintain the balance of the equation, what you add on the left-hand side should be added on the right-hand side. Sorry, this is a9. Therefore, now you know that the left-hand side is a perfect square. It's a complete square. That's what it means to complete the square. And we can write it in the form x plus 3 all squared. And this equals 7 plus 9, which is 16. And now we take the square root of both sides, giving us x plus 3 equals plus or minus 4, which makes x equals negative 3 plus or minus 4. Therefore, x equals either negative 7 or 1. Again, x squared minus 10x equals negative 4. We complete the square by adding 25 to the left hand side, and to maintain the balance we need to add 25 to the right hand side as well. Therefore, the left hand side is now x minus 5 all squared, and this equals 21. Taking the square root of both sides gives you x minus 5 is equal to plus or minus the square root of 21, and therefore x equals 5 plus or minus root 21. You can either leave this answer in this form, this is what we call the exact form, or you can calculate root 21 and find out what the answer is to any given degree of accuracy. Let's solve this by completing the square. The constant is on the left hand side, So in order to make life easy for us, what we can do is say x squared plus 8x equals 10. So we send the constant to the right hand side, and then we complete the square. X squared plus 8x plus 16 is equal to 10, and you have to add the 16 here as well. Write this as a perfect square. X plus 4 all squared equals 26. Take the square root, plus or minus root 26, and therefore x is equal to negative 4 plus or minus root 26. And finally, we find that we have two constants in this equation, and what we can do is x squared plus 5x is equal to 12 minus 1, that's 11. Then we add x squared plus 5x. We have to add 2.5 squared to both sides. Now on the left hand side, we really do not need to calculate what this is. We can simply factorize by writing x plus 2.5 all squared. And this equals, now you have to calculate this constant. This is 6.25 plus 11, and that's 17.25. Take the square root of both sides, gives you x plus 2.5 equals plus or minus root 17.25, and then x is equal to negative 2.5 plus or minus root 17.25, and you can use your calculator to evaluate the two possible values of x. One last remark is that if you have something like 2x squared plus 4x minus 15 is equal to 0. Now remember that we can only complete the square if a equals 1. So in order to do that, we have to divide through by 2, which is the coefficient of x squared. So dividing term by term, we get x squared plus 2x minus 7.5 is equal to 0. Take the constant to the right hand side. X squared plus 2x equals 7.5. What do we have to add? Half the coefficient of x is 1. Squared is 1. So we add 1 to both sides, giving us x squared plus 2x plus 1 equals 7.5 plus 1. The left hand side can be written now in factorized form, x plus 1 all squared, and it equals 8.5. Taking the square root, don't forget the plus or minus, and subtract 1 from both sides, gives you x equals negative 1 plus or minus root 8.5. And then if you want to calculate this on the calculator, you can do so. And that's it.